All right, so well, thank you all very much for coming out on this actually gorgeous football Saturday. Got my football here. I am from Ohio State, so I'm a big football fan. I'm an Illinois fan, but mostly in the other sport, the round ball sport. So as Naomi said, I'm going to tell you today about some, let me switch over here. All right, maybe. Okay, I want to talk to you about a very interesting set of materials which are called superconductors. How many people have heard of superconductors before? How many have ever held in your hand a superconductor? Okay, lead is a superconductor. Aluminum is a superconductor. Story. It's a very big story on this campus, as I'll try to tell you. And it's a continuing story. There are a lot of things going on that have kind of revived our interest in this. I've been doing this for about 40 years now. And every 10 years or so, the field ends, and they declare it dead, and then it comes back. And so it never seems to go away. And so right now, we actually have, I think, a very exciting time. There's a lot of new materials. There's a lot of things we don't understand. There's a lot of potential for this. This picture kind of represents what has been a quest, I guess you might say, of our group to understand the exotic nature of these superconductors. And I'll say a little bit more about what that means as I go along. So first, a state that has zero electrical resistance, and I'll say a little bit more about where resistance comes from. But we know what that means. If you take a wire normally and you put current through it, what happens to it? It heats up. Okay, so and that's a very good thing if you want to make a toaster, because you put current through it, it heats up, you dissipate power, and the electrical resistance is a characteristic of that material that makes it heat up. When something has zero electrical resistivity, you can actually transport current without any dissipation of energy. And I think you can already think that's a really good thing for some systems. Things like magnets, high field magnets, power transmission lines for the energy crisis. And this phenomenon occurs only below some temperature. So we'll talk a lot about resistance, we'll talk a lot about temperature. And what I want to do really is tell you a story about superconductivity. It's a story that starts with its discovery, winds through a lot of things that I had nothing to do with, happened long before I was born, happened certainly long before most of you were born, and then eventually ends up in some things that I was involved in, and then ends up where we are now trying to come up with some applications. So this is an interesting story, I think. There's a lot of history in superconductivity. There's a lot of very interesting characters, some of whom are in our own department here at the University of Illinois. There's some intrigue, some controversy, some plot twists. There's multiple storylines, but the most important thing of all, there's no ending to this story. It continues on, and every day we get more excited by this field. Okay, so there's a sort of a subplot to this story, and that is my own involvement in it. And I think the point I sort of want to make in this series, as you think about maybe being a physicist someday or interested in physics is a story itself. And every one of us who's in physics has their own story. I got to where I am today not by any decision I made. I didn't wake up someday and say, I want to be department head and be here on Saturday morning giving a talk. You just sort of make decisions along the way and you end up somewhere, and you're influenced by people that you meet. So my story is pretty simple. This is my whole life on one slide. I was born in Kettering, Ohio. Anybody heard of Kettering, Ohio? Yes, suburb of Dayton. I went to Ohio State University. Not quite as good a physics department as us. Usually a little bit better football team, although not so sure right now. I went to England for a while, for a year. I went to Berkeley for a couple years as a postdoc, came back here to the University of Illinois, and except for one sabbatical to Berkeley, I've been here pretty much for the last 28 years. This is the center. The University of Illinois is the center of the universe in superconductivity. If you go anywhere in the world and say, I'm from Urbana, they will say, I know Urbana, because that's where superconductivity was understood. So this is a really important place in superconductivity. It's a really pleasure to be here and working in this department. Now, like most good stories, this story has a prologue. And I want to take a little bit of time here to just simply say, not that. That wasn't true. I actually love physics. That's why I'm here. But in starting this series on this whole Saturday Physics Honors series on physics, you're going to hear from a lot of different people. as I go around to travels and people, I say, you know, you sit next to somebody on the plane and you say, what do you do? I'm a physicist. You know, they go, oh God, you know, I hated physics. So that's the main reaction people have who took physics. The second reaction is, I actually don't know what physicists do. So if you ask people, they'll mostly say, well, we slide balls down inclined planes or carts down inclined planes. Or we work in labs. This is a picture of my lab. Down in the materials research lab, and we work in dark labs and do mysterious things that nobody wants to talk about. Or what do you think physicists do, mostly? We blow stuff up, right? That's what physicists do. And so today we'll blow some stuff up just because that's what physicists do. And so I tried to think, what is physics like? How could I tell you what it's like to be a physicist? So the first thing I thought, well, of course, physics is like football. And it is, because physicists, football coaches draw little diagrams like this. And you know, they draw little plays, and sometimes they work brilliantly. Look at that. The guy's scored. That's this guy, an Illinois guy. I don't know this. So it looks, you know, it works. But most of the time, it doesn't. You get sacked, you get killed. And that's what experimental physics is like. And I want to, this is sort of a disclaimer in a sense, because I brought a lot of toys from my lab here today. And we're going to do some experiments, and probably some of them won't work. And that's just sort of the nature of the business. But it's not exactly like football, because for one thing, the physics department here is ranked 8th in the country. And the football team is not so highly ranked, actually, right now. Although maybe by the end of the year we will be. The other big difference is they built these beautiful stands here. It's Memorial Stadium. And they charge lots of money for people to sit there and watch people play football. Well, so far no one has offered to buy tickets to see my students work in my lab. But if anybody's interested, we got a chair and you're welcome to come down anytime and watch us do physics. Watch what we do. Well, then I thought, well, physics is like wine. I'm kind of interested in wine. Wine's an interesting material. It's very complex. And it starts like physics with good samples. In this case, good grapes. And then you have to work really hard. And when you're done, you can make lots of different kinds, just like there's lots of different kinds of physics. And it takes a long time. Wine is a process. You put it in, you let it sit for years and years and years. That's the way physics is. This story I'm going to tell you started 100 years ago. 100 years ago. I've been working on it for 40. It's not something you do overnight. And the other thing I think that's interesting is if you're into wine, one of the things winemakers like to do is mix different kinds of wines. They take different grape varietals, they mix them together, make things that are different. And that's what we're doing here. It's called interdisciplinary research. Physics is not isolated. We work with chemists, we work with biologists, we work with computer scientists, material scientists. Actually, we work with lawyers, finance people, education people. And what's coming out of that is a lot of institutes and things on the campus. So if you're here for the day or can visit at some time, there are a lot of things to see on campus. And a lot of the activity in superconductivity is in this interdisciplinary research. But then I decided that physics is really like MapQuest. So, or Google Maps, whichever your preference is. Everybody's used Google Maps, right? I mean, it's a great thing. If you haven't, get on there and just do it. You can. So the idea is with Google Maps or MapQuest is you can zoom. You can zoom around. So here's a picture of Champaign-Urbana where we live. We're located right now about right there. We can zoom out. We can see the state of Illinois. We can see the country. Or we can zoom back in. We can see Champaign. We can see the campus. Here's the football stadium, assembly hall. And we can zoom into where we are right now. And this is Loomis Laboratory of Physics. This is where my lab is, in the Materials Research Lab. I already showed you a picture of that, where we work. And here is about where you're sitting right now, at this star. So physics is like this because what physicists really do is they zoom. They zoom around. Except we have a really big scale. In MapQuest, you go from a few meters to hundreds, thousands maybe of kilometers. In physics, we go from the size of the universe, 10 to the 26 meters, to the size of the smallest things we know, which are quarks. Kevin will tell me that's not right. There's things smaller wherever he is. But so anyway, that is, if I do the math here, 45 orders of magnitude that we zoom. So our scale is really big here. If you're an astrophysicist, you zoom out. You look at the biggest things in the universe, planets, stars, galaxies, clusters of galaxies. Study things like black holes. If you zoom out to the beginning of time, where you can see the Big Bang and then what happened since then. We have people in our department involved in things like the Planck telescope to look at that. If you're a high-energy or nuclear physicist, you zoom in and way in to the crystals, to the atoms, inside the protons, inside the quarks, to see the interactions that occur there, and they study these interactions at the very, very shortest scales. And they do that with the very biggest tools. Kind of funny, right? The smaller you want to see something, the more money it costs. The bigger thing you have to make. This is a picture of the Large Hadron Collider. How many people have heard of the Large Hadron Collider? Okay, it's been in the news a lot, mainly because it started and then blew up, like physicists do. That wasn't intended, so the idea is you get particles going around here, look at interactions in these detectors. Here's the beamline, and you use the biggest tools to look at the smallest things. Okay, so where do I live? Where do condensed matter materials physicists live? Well, we zoom in, but only part way. We want to zoom in to where we can see the interactions that occur on a very short scale, but not so far in that we lose the interactions of all the atoms around it. There's a word for this. It's called mesoscopic. Meso means middle. So we don't want microscopic, the really smallest. We don't want macroscopic, where everything averages out. We want to get to this scale where you can sort of see things happening, and you keep all the interactions, but you don't throw the baby out with the bathwater, as they say. In other words, you don't lose all the information about the collective materials here. This is also known as the nanoscale world, a word that has gotten a lot of attention lately, because we can now make things. This is a picture of a device in our lab. This is about a micron apart. Give you an idea, human hair is about 50 microns in diameter, so this is a hundredth or so the size of a human hair. It would look like this on this scale. Now, what happens when you're at that scale is you run into the world of quantum mechanics. Quantum mechanics is the way things work in the world, but you only see it manifested when you get down to really small scales. And so a lot of what I'll talk about today is really governed by this quantum mechanics. I'm not going to try to explain that. It's often said there are only two people in the world that understand quantum mechanics, and they actually don't agree on what that explanation is. And I'm certainly not one of them. But one of the things about quantum mechanics is it talks about something called the wave-particle duality. Now, we all know some things about particles. I brought a baseball here. It's a particle. It has a mass. It has a position, velocity. We can do a lot of nice experiments with that. And we also know about waves, water waves, electromagnetic waves, waves on strings, guitar strings, for example. But in quantum mechanics, these two things blur together. And what we learn is that all waves actually have particle properties. They're quantized, that's where the word quantum mechanics comes from, in discrete units. And we give them names with ONS on the back. Photons, magnons, protons, or not protons, that's the wrong one. Photons, magnons, all kinds of other things that are to describe the fact that these extended wave excitations act like particles. And then in turn, particles have wave-like properties. And those waves are called wave function. They exhibit a property called interference. And I think most of you probably know what interference is. Interference is a characteristic property of waves, and it's due to the superposition of waves. Here's a picture here, very simple. You drop a couple drops of water in, the waves spread, they interact. Where the waves come together, the amplitudes add, and you get a crest or a peak. And when they are out of phase, you get destructive interference and you get troughs. Now, the reason I bring this up is that a lot of the experiments I'm going to talk about today are actually interference experiments. And the wave-particle duality is something that is exhibited both by waves and by particles as a result of this wave-particle duality in quantum mechanics. So an example of an interference experiment is if I take a single slit of a diffraction, a small slit through an aperture of some kind, and I shine light on it, what you see would be a pattern in which there are interference effects, in which you would get a large peak in the center and a lot of modulations. If you took two slits, you would get constructive interference in some places, destructive in others, and you get a wave front that modulates. And here's an example of that actually in water waves. You have two slits. You see the waves from each one. And you can see where they interfere. You get peaks and valleys as these things modulate. So again, the reason I bring this up is that I'm going to show you some experiments. And I want you to know that they're essentially interference experiments. They'll have patterns like this. But they're actually, what is interfering is the wave functions of the actual particles, the superconductors, the Cooper pairs, we call them. I'll get to that definition in a moment, which are parts of the superconductor. Okay, so let's start our story on superconductivity. And superconductivity was discovered almost 100 years ago. In fact, we're gearing up right now for a really, really big party. One thing we like to do in the physics department is party. And so when there's something that happens, 100 years, 2 years, 4 years, any significant date. But this is a big one. 100 years since superconductivity was discovered by a guy named Heike Kamerlingh-Onnes in Leiden, a little town in the Netherlands. Really neat place, actually. And he was actually the first person to liquefy helium. Helium is we know mostly as a gas, but you can liquefy this by putting it under pressure. And in fact, I have here a couple tanks. Here's a dewar full of liquid helium. You probably have seen liquid nitrogen. I'll throw some around in a little bit. But here is a dewar full of liquid helium. He was the first one to liquefy that. That's the actual liquefier. You can see that if you go to Leiden in a museum there. And as I said, we just celebrated the 100th anniversary of the liquefaction. We're now gearing up for the 100th anniversary of superconductivity. So Kamerlingh-Onnes actually did something else. He invented the field of cryogenics. Cryogenics means low temperature physics. And there are reasons why physicists like myself want to go to very low temperatures. And there are really, I guess, two reasons. One is that you get rid of thermal motion. Due to energy, heat, at a finite temperature, things move around. Atoms vibrate. It confuses you. It's all you see until you get down to low temperatures. The other one is there are sometimes new phenomena that occur, and they only occur at low temperatures. When the thermal motion's out of the way, and the interactions in these quantum mechanical interactions, mesoscale interactions I talked about, take dominance, and you can see quantum mechanics manifest in macroscopic objects. So Kamerlingh-Onnes found really the most remarkable new phenomena I think anyone has ever discovered, and that is the fact that some materials go to zero resistance at some temperature. And here's the actual graph. You can actually look it up in the journal. And the first material he was looking at was mercury. Mercury, of course, we know is a liquid, but at these temperatures it's a solid. And he measured the resistance, and it went to zero. And he showed that this was zero resistance, and it onset at some particular temperature, which was actually... We know now that mercury is really 4.5, but he said it was 4.2. We call this the transition temperature. That's the temperature at which the material becomes superconducting. Superconducting at low temperatures, it's a normal metal at high temperatures in this range. So, is that a rare phenomenon? No, actually it's not. In fact, most metals, most things that conduct, become superconducting. So here's a periodic table. This is where physicists live. It's the first thing I downloaded to my iPhone when I got it, was a periodic table. You cannot be without a periodic. How many people are carrying a periodic table? Great. You're physicists. Or maybe you're chemists, but that's okay. We let them come too. So here's the periodic table, and all the blue ones here are actually superconducting. You can see it's most of them, and the ones that aren't actually become superconducting if you put them under enough pressure. So they want to become superconducting. I'll come back to this graph perhaps in a little bit here, but it's interesting that there's a couple classes of materials that are not superconducting. Not many, but notice what they are. They're magnetic things, and they're what we would call good metals. Copper's the best. Copper, gold, silver. These are all some of the best conductors we know. Why would they not go superconducting? That's an important clue to what happens, why superconductivity happens. It turns out that you can make alloys, you can make compounds. There are more than 1,000 things that are known to be superconducting. It's actually more remarkable most of the time when things don't become superconducting. Okay, so let's just say a little bit about what electrical resistance is in case you're not so familiar with this. One thing that physicists like to study is transport. That means how do electrons move through a material? Turns out if you had a perfect crystal, where the atoms were all on their right positions, an electron could move very nicely through this and not scatter, not run into anything, not create any dissipation. You could essentially have zero resistance. That, of course, never happens. It doesn't happen because of lots of things. It doesn't happen because there are crystals are not perfect. They may have impurities, they may have vacancies where there's atoms missing, they have faults, dislocations, and even if they don't have any of those things, they have surfaces. They're finite size. The surfaces act like something that electrons can bounce off of and scatter off of. Even if you had an infinite crystal that had no impurities, had no vacancies, had no dislocations, absolutely perfect, wonderful crystal, it still would not show zero resistance because there's atomic motion. The nuclei vibrate. This is due to the thermal motion. We actually give that a name. As I said, we call it phonons. They're vibrations of the lattice. You can sort of think of a lattice as a bunch of masses hooked together by springs, and they're always vibrating. They're wiggling around. They're out of position a little bit. So when they're out of position, or there's impurities, a different atom, or there's vacancies, in a real crystal, electrons scatter. They don't move through in a straight line. They work their way through the crystal. This gives you energy dissipation. This gives you voltage, and that's the origin of resistance. Okay, so what is resistance? You put a current through a material, you measure the voltage. The power dissipated is V squared over R, or I squared times R. The resistance versus temperature tells us a lot about these things, what is happening in the material. So one thing physicists like to do is measure resistance versus temperature. That's what Camerlingh-Onnes was doing. He didn't read in some book, oh, it might become superconducting if I went to low temperature. In fact, that was the last thing he would have thought. He wanted to measure some materials and see what they were going to do. So, for example, it's generally thought that, or it's known that if you have a dirty metal, there's a lot of scattering, the resistance is pretty much independent of temperature. If you make the metal clean, the only thing you see at high temperatures is it goes linearly in temperature. That's due to the phonons, the lattice vibrations, which are vibrations are scaling with the temperature. As you lower the temperature, it slows down, gets more perfect, the resistance drops, but then you run into the problem, the same one here, you run into the defects in the material. And if it's a semiconductor, things like graphene's a semiconductor, silicon, germanium, then you actually have hopping. And so you actually get lower resistance when you're at higher temperature. You need the temperature to, you're stuck in wells. You need the temperature to be able to move to the next location. You've got to have some thermal energy to move you along. As you go to low temperatures, you don't have the thermal energy, the resistance actually goes up. So Camerlingh-Onnes was trying to see which of these actually occurred. Of course, what he found was something more remarkable. The resistance went to zero. Okay, so we're going to try to measure resistance versus temperature here. Again, it's an experiment. We'll see if it works. But first, we need to talk a little bit about temperature. So here are the three common temperature scales. This is the one when we were first introduced to this. We talked in Fahrenheit temperatures and freezing point of water, boiling point of water, and we live around on what is today 70 degrees or something, Fahrenheit. And then we learned about centigrade scales. But physicists like to work in something called the absolute temperature scale, or the Kelvin scale. The Kelvin scale is important because there is, in fact, a zero of temperature. There's a temperature at which all this thermal motion freezes out. That's called absolute zero. In Fahrenheit, that's minus 454 degrees. How many people have ever seen a thermometer read minus 454 degrees? Some days in Urbana it seems like it, but not really. In centigrade, it's minus 273. So here's the Kelvin scale. The reason we like this scale is this is essentially a measure of the energy in the system, of thermal energy. It starts at zero and goes up to higher levels. Superconductors live here. The highest superconductor known has a temperature, critical transition temperature of 160 Kelvin. That's a new superconductor. It's not the ones that I'm talking about right now, but I'll get to those. But the ones we're talking about now live around this liquid helium, around 4.2 Kelvin. Now, to get to these temperatures, we have to use cryogens, either liquid nitrogen or liquid helium. So one thing we're going to do today is play with some liquid nitrogen. So here I have some liquid nitrogen here. Liquid nitrogen is at 77 Kelvin. It's fun stuff because it vaporizes as soon as you pour it on the floor. We use this to clean our floors. Pushes the dirt out of the way, pushes it to the corners. Liquid helium, of course, is very cold. You can take, here's my glove. I blew up here, and when you put this glove full of air into liquid nitrogen, it compresses the air and reduces the size of it. It also gets rather crispy. You can see, and this will blow back up. Here's a balloon. These are just fun things you can do with liquid nitrogen. This is what physicists do also. So you can see the air is freezing out of this balloon. Liquid air, actually, nitrogen freezes at a much, is condensing and freezing out, and so this will blow back up. My student asked me to do this experiment. Here's an ordinary rubber ball. What is this, a racket ball or something? Let me drop this into here. Let that cook for a minute, opposite of cooking. And now you can see it's actually pretty hard here. So now it doesn't bounce. It just sort of thuds. So one thing that liquid nitrogen does, and I've got lots of liquid nitrogen up here, so after the lecture, if you want to come up and play, that's one of the things we have the most fun with. One thing that liquid nitrogen does is when it warms up, it expands enormously. So I have here a little cannon. Always lots of fun here. So people in the, cover your heads here. So I'm going to pour a little liquid nitrogen into the cannon. And I'm going to take a cork, put it in there, and give it a little whack here. And then when I close this off, see, I knew we would kill someone with this experiment. Are you all right there? We have liability insurance. Don't worry about it. Let's do this one more time, and let's not close it off before we do it. How about a little more of an angle here? All right. Well, that looks like a fun experiment. We can try to hurt someone here.
Is that how you wake up students?
Yeah, exactly. I just knock them off and bring them in. So we also, I learned this from Matt Sellin, one of my colleagues here. You put a little liquid nitrogen in the bottle, not very much. Put your hands here. You seal this off. Put it in here. I don't know if it actually sealed. I did it pretty fast because I didn't want to get killed. I think it's hissing. All right, well, we'll do that one later. If that blows up later, we'll know why. Okay. All right, so let me try a real experiment. So what I want to do is see if I can measure here resistance versus temperature. And here's a graph. And we'll start this up. So what I have here is a helium dewar. I've got a probe here, and I've got a thermometer, which is reading. Let me start this. So this is reading the temperature right here, 270, and this is in Kelvin. So now we're in centigrade temperature, slightly below zero. And we're reading here the resistance of a piece of niobium wire. So let me go back just a second here to the, I lost my probe here. Let's see, go the right way here. Okay, so here's the periodic table I'm looking for. And here is mercury, the first superconductor that Camerling Onus looked at. We're going to look at niobium, which is over here. It's the element with the highest transition temperature, about 9 Kelvin in this case. So we're going to try to measure resistance versus temperature for niobium. So what I'll do is I'll start lowering this in. And what we should see here is the temperature will drop and the resistance will drop, because it's a metal, and it's roughly going as linearly in temperature as we cool down. So we're at 258. We can put back the temperature scale here so we can see how we're doing. So we're coming down here in temperature. So 219. Just a little bit more. We do this slower if we were in a real lab, but we don't have time, so here we go. And you can see it's basically going linearly, but it's actually fairly flat. It actually looks more like the disordered metal. You can see it's hard to read the scale here, but this is 256. So it's only dropped really about 10% in its resistance, even though the temperature has gone from 300 Kelvin to about 100. So the temperature's dropped by a factor of 3, but the resistance has only dropped by about 10% or so. So it's really going fairly flat. Now we're speeding it up. Getting noisy for reasons I have no idea. All right, let's see how we're doing here. And look at that. So the resistance precipitously dropped at that point from, again, I can't read the scale up there, 230 ohms in resistance to very, very close to zero. The reason it's not zero is have a little bit of lead resistance in this circuit. So this is a superconducting transition, and that is a piece of niobium. And so this is still something that I've been doing this for 40 years. That is still a remarkable thing, to take a metal and see it go in that transition. And when you're making new materials and you see that happen, you obviously get very excited. Now I have a piece of copper, too, that we could measure. Let me just warm this back up. We might try that here, and if I can get this back up. And this will warm up. You can see it'll trace pretty well. It goes back up. It's already gone back up through the transition and is warming up. When that gets a little bit warm, I'll switch the leads and we'll look at copper so we can take a look at that. So if you've never seen anything go superconducting, now you have. And it's a remarkable phenomenon. I certainly, for Camerlingionus 100 years ago, this must have been, in fact, I think he probably thought it wasn't right. I'm sure he said something's wrong with my experiment. Okay, so let's move on here and talk a little bit about other superconducting things. So first of all, the Meissner effect. So it turns out superconductivity is not as simple as just zero resistance. So in 1934, Walther Meissner discovered that superconductors also expel magnetic field from their insides. This is a phenomenon called diamagnetism. And so it means it's more than a state with just zero resistance. The field, the magnetic field inside, is actually expelled. The field goes around. And this, of course, is how many people have seen magnets levitated? Okay, we'll do that here just so we can show it. Let me see if I can get this to work. You want to just switch on to that, and I'll get some nitrogen going here. So we have sitting around the lab lots of little pieces of this is actually a high-temperature superconductor. I'll get to those in a minute. So a piece of black material. We can put that in liquid nitrogen because it has a high enough temperature. And so when the material becomes superconducting, you can see that the little magnet there, once we clear away the frost here, is actually levitating. We can play with it a little bit here, give it a little spin. So levitation, there we go. So levitation occurs as a result of this diamagnetism. And so the idea is that if you have a magnet, and we do have some magnets here, but I think I'll just move on for time here. So in a magnet, the important thing to remember is opposites attract. So north and south poles attract, north and north poles in a magnet, the magnetic field repel. If you have a non-magnetic material, something like aluminum, then there's no forces when you put a magnet next to the material. If you have a magnetic material, like a piece of iron, you magnetize the material in the same direction that the magnetic field is applied. That creates an attractive force, and these things would draw into each other. In the case of a diamagnet, which is the case of a superconductor, since the field is being excluded, the magnetic field from the magnet is opposed by an internal magnetic field inside the superconductor. That creates a situation where opposites, or the same poles, repel. You get this repulsive force. This enables this little magnet to levitate over top of the superconducting material. So that's the basic idea behind the Meissner effect, and it's a very important phenomenon that tells you a little bit more about what's going on inside the superconductor. Now, I couldn't resist showing here a little film that I came across. So this is the levitating train, and let me blow this up a little bit more here. So here is a superconducting train, and this is something that people actually think about. One application of superconductivity might be to make trains. And you can see this is a little compartment with liquid nitrogen in it and little superconductors like the ones I have. And they have it over a track, which is a magnet, a set of magnets that goes around. And they show it how it works here, same thing that we have. Let me move this along a little bit. Show you some of the other neat stuff here. So there they are cooling it in liquid nitrogen. And I just want to show you this actually will also work, levitation also works to create forces which can actually hold things up. Well, here's an interesting experiment. The person puts a piece of paper, of course it goes right over it because it's not touching the track in this case. Or here's a little piece of stuff, a little bit more, see the challenge, it goes right over top. So kind of an interesting film, I think. Pardon? It doesn't leave the track because of the way the track is made. It actually has a series of magnets. There's actually a picture in here that shows this, if I can find it real quick. I thought it was in here somewhere, but they actually show in here how it's actually as a point of stability, that you can't move the I'm not finding the place where they show this, but so it really has to do with the fact that the field lines curve in such a way that if you move it, that's actually true here if you see as well. We're probably warmed up now, or I took it off the picture, but yeah, it's sitting here. It actually has a point of stable equilibrium, because the field lines bend in a certain way, so it's not free to translate across the surface. I want to show one last thing here. You can actually, here's an interesting picture where they actually show this train on the side here. It's actually, again, held in by the potential, so it's not only held up, but it's held against the building. And their idea is that you can make subways and you can move people around on the side of buildings. I think it's a pretty interesting trick here. So it's a pretty neat track. You can see the track's fairly complicated. It has a series of magnets to bend the field lines in such a way. Pardon?
If you have a power loss situation, you don't want to be in that train.
That's correct, yes. I don't know how they avoid that problem. Hopefully someone would take care of that. There's actually a lot of really neat stuff like that on the internet if you play around with that. Okay, so let me get back up here. Okay, so now what I want to do is talk a little bit about the theory of superconductivity and then some of the more exotic materials that we have. So here is the three people who were here at the University of Illinois. How many people have heard of John Bardeen? Okay, you should know about John Bardeen because he's probably the most famous professor ever from the University of Illinois. He's the only person to have won 2 Nobel Prizes in the same field, in physics. He invented the transistor, and he also discovered the theory of superconductivity. So we actually honored him, the important paper they did in 1957. We had a nice conference here a couple years ago. We had, I think, 9 Nobel laureates here to talk about different things involving superconductivity. So how does superconductivity work? Well, normally what you have is you have repulsive forces between electrons, but they're overbalanced by attractive forces caused by lattice vibrations. So I'll show you how that works in a moment. That allows the electrons to pair into what we call Cooper pairs, named after Leon Cooper. Those pairs can then condense into the single quantum mechanical state described by a wave function. And that was what I was talking about before, the wave properties. And I'll show you some pictures from that in a moment. But we can have all of the electrons in the system acting as a single quantum mechanical state. And this allows the system to condense into a state which can carry supercurrent without resistance. So that is why you can have this current transport without running into things in the material. It's this quantum state, and it starts with this interaction between electrons. Now, I'll say some more about this in a moment, but the pairing is what we call isotropic. It's the same in all directions in the material. And the reason that's important is the new superconductors are not isotropic. So this defines what we normally call as conventional superconductivity. So let's see how this works. So normally electrons, they're all negatively charged. They repel each other. They don't like each other very much. And so in a metal, if you put a positive ion in, the electrons are both attracted to that. So even though the electrons are intrinsically repulsive, this creates an attractive force between the electrons mediated by the lattice vibrations. And this we call a Cooper pair. So it's the interaction of the electrons inside the crystal. And that's why we don't want to take the material apart and look at electrons. Electrons don't cause superconductivity. Ions don't cause superconductivity. It's a fact they're all in this together. And it's referred to as a many-body phenomenon for this. So let me try to explain how this works sort of in another example. So imagine that, how many people here from high schools here? Okay, so let me get a couple volunteers. How about this young lady right here? Very good. Who else was from high school? Over here, this young lady right here. That would be great. And gentleman right here. All right. So this is how it works. So what's your name?
Laura Orlando.
Laura, where are you from?
Uni High.
Uni High. Okay, Laura. And you are?
Kareem.
Kareem, and you're from? Uni High. All right. And you're from Uni High? No. No, good. You're our?
Urbana High School.
Urbana High School. What's your name?
Zita Hubler.
Zita. Okay, so you stand back there. Handsome. So I got two attractive young women here. And so imagine you don't like each other very much. All right, good. See, it's working already. You can't stand to be in, more than that, you can't stand to be in the same room. Each other. There you go. Okay, that's good. All right. So if you go, you never see these two people together. They just don't want to be in the same place. They're like electrons. But then comes, your name was?
Kareem.
Kareem. Now, Kareem, very handsome young man. Kareem comes into the picture, and you like Kareem. So what happens? All right, and you like Kareem. So what happens? Look at this. It's working. So the two repulsive interactions are now mediated by Kareem, this handsome ion here, in the moment. Now, once they're in this package, they lower the whole energy of the system. The whole energy of the system is now lower. They can actually now form this quantum mechanical state because of the bonding of these two into Cooper pairs. You're now a Cooper pair. And you can move through the lattice without interacting. Thank you very much for your help. Very good. Let's give them a hand. So Kareem plays the role of the ion and couples the two electrons together. That's a very simple example of how you can get attractive forces arising from intrinsically repulsive objects. And this is sort of the basis for this unique quantum mechanical state, which is superconductivity. Okay, so this theory, as I said, was in 1957, and this really explains superconductivity. Well, this is where I entered the field. The next most important thing in the history of superconductivity is I became a graduate student at Ohio State, and I went into the lab, and what I was told is superconductivity is over. It's understood. We know everything about it. The highest transition temperature went from mercury, here's niobium that I showed you, went up to 23.3 degrees, and that was it. It wasn't going to go higher. You could calculate it couldn't go much higher, and the applications are what took center stage at that time. So I didn't get too much involved in materials, which I am involved in now. I was involved in things called Squids. Now, Squids stands for Superconducting Quantum Interference Device. It was actually based on something called the Josephson Effect, discovered by Brian Josephson in the mid-60s. And the basic idea is this is essentially, if you want to think about it, that's a squid. That's just for fun. The squid is sort of the transistor of superconductors. In the semiconductor industry, in your computers, your cell phones, all the things you're carrying with you, the electronics that are going to mess up my next experiment in the room, the workhorse is the transistor. It's a semiconductor device. You can control the current. You can control the current through this channel by applying a current through the base of the transistor. And this was, in fact, invented by John Bardeen. Here's a stamp. Anybody ever seen the John Bardeen stamp? This was released a few years ago, and it shows John the physicist with a picture here of the transistor. Well, in a superconductor, you make a device with two superconductors separated by an insulating barrier, and you can actually put current through this without any dissipation as a result of the quantum mechanical properties of this object. You can control this in a system such as this. You can put a loop, and then by applying a magnetic field to this loop, you can actually modulate the critical current, the current that flows through this device, with magnetic flux. So it's like a transistor. You can control the current with some external object. You can do that either in a single junction or in a squid device. Now, squids are actually very important devices. They have enormous sensitivity. They can detect fields as small as about 10 to the minus 6 of the Earth's field, a millionth of the Earth's magnetic field. Magnetic field in this room is about a Gauss, half a Gauss, something like that, which is 10 to the minus 4 in Tesla. They can detect currents as small as 10 to the minus 10 amps in a very low resistance. They can detect voltages as small as 10 to the minus 14 volts. And they're used for all kinds of different things: communications, detectors, neuromagnetism. You can take a squid and measure the currents that flow from neural circuits in your brain. And you can use this as a way to kind of non-invasively test how things are working. You can look for geophysics. You can look for water deposits in the ground, magnetic deposits. You can look for earthquakes as things move. It's the basis for the voltage standard. You can use it for quantum computing. There's a lot of things in cosmology, a lot of applications of squid devices. Okay, so we have, oh, you're going to set up my oscilloscope? Good. Ah, beautiful. So we have a squid, I think, set up here. All right, and that's reading the output of my squid. So the squid is located in this dewar. This is another helium dewar. It's full of liquid helium. I have a squid device that looks just like one of these. It's a loop with two superconductors. And I have a big magnetic field coil that I can couple things to in this device. And I've got a cable, and it runs to some electronics, and then eventually it's hooked to the circuit. And here is reading out the output of the squid voltage. Now, the way this works is I need to find a magnet somewhere. All right, so I got this little tiny magnet here. And if I walk over here by the door, you can see I can move this around and I can change this. I found a little bit earlier that the best magnet I had was actually my cell phone case. Every time I walked over here, it would actually perturb the system. So this is measuring the magnetic field from my cell phone case as I move this around. And so this is a magnetic field detector. It can be used, as I said, for all these different applications. So we have a little demonstration set up here. So in the back up there, I have a little magnet on a string hanging there. And if someone, Inga, maybe, could you wrap around there and give that thing a twist? Just wind it up a little bit. There you go. Okay, so now you can see we're detecting the magnetic field from that magnet clear up here in this little dewar. And if you watch here a minute, it's going to slow down. And then it'll wind up and start going the other way. You can see the magnetic field being detected from that device. So this is a squid detector. They are incredibly sensitive devices. I can mess it up here with my own magnet by getting in the way there. But so it's a device we use a lot in our labs for lots of experiments. It's used for a lot of fundamental measurements. And it's the basis for the set of experiments that I'm going to tell you about in a moment, which is how we discovered some interesting properties of the superconductor. So there's a squid. You're welcome to throw things around. If you've got nails in your shoes, it'll pick that up. If you've got keys, it'll pick that up. If spinning my keys here, it's picking up the magnetic field from these keys. So very interesting devices, and one of the big applications for these is for things like MRI applications. You can use them for medical applications, for detecting things. People are looking at squid detectors for looking at cargo, for looking for objects that might be in there, magnetic properties of things. Okay, so the field of superconductivity, as I said, when I was in grad school, I was told superconductivity is over. Find something else to do, is what they said. Well, I didn't do that, and I stayed the course. And the whole field changed dramatically in 1986 with the discovery of a set of materials by Alex Mueller and George Bednorf at IBM in Switzerland, where they discovered a set of materials where the superconductivity transition temperature jumped from 23 up to initially 35, and then 100, and then all the way up to 160, with a set of materials that are the most unlikely things you would ever think to be superconducting. And those are these materials I've been showing you. These are actually, this is a piece of YBCO. It's a ceramic. It doesn't look like a metal. It looks like a charcoal briquette. And if anything, if you ever thought something could revolutionize the electronics industry or the power transmission industry that looks like a piece of charcoal, it's really kind of a remarkable thing. But there's the superconductivity. And in fact, at that time, we had a party. That wasn't this one. That was a different party. But you probably, how many people were at Woodstock? Oh, come on. Somebody must have been at Woodstock. I always say I was, but I wasn't. Yeah. So anyway, Woodstock was the great celebration of music. It lasted 3 days, had 33 acts, and 500,000 hippies at that time. Okay, so we had the Woodstock. It's known as the Woodstock of physics. So just the year after the discovery of superconductivity, at the March APS meeting, American Physical Society meeting, that's the meeting of physicists. Scary meeting, but they had a session, and 2,500 physicists came. 8 hours of continuous talks. It started at 8 p.m. and lasted till, I think, 4 in the morning. And there were at least 50 talks, actually there were more than that, I think, of people talking about what they had done in 1 year. This is how dramatic this was. This is probably the singular event in condensed matter physics in my lifetime. Because think about what was happening here. This material took the transition temperature up by a factor of 5, basically, or more. Someone announced at that meeting, our lives will be changed. Well, that wasn't really true for all of your lives, but it was for the physicists working on this. This has really changed everything in condensed matter physics. It's made us realize we don't understand superconductivity. We don't understand condensed matter physics. It's opened all kinds of new materials for research. And it's launched a whole new era for superconductivity in which real applications like power transmission lines are actually possible. Okay, so here now is where we stand right now. Actually, there's one class that I don't even have on here yet, of superconductors. And I said lots of things are superconductors. You can see this series that I already pointed out to you before, starting with in 1911, discovery of mercury. And then the transition temperature crept up slowly. There's a new member of this group discovered a couple years ago called magnesium diboride. Looks like a salt, but it's actually superconducting. Here's a set of material. This is the high temperature superconductors. There's things called fullerenes. These have the crystal structure. They're actually carbon-based materials with the crystal structure of a soccer ball. Buckminster fullerene, and that's why they're called fullerenes. There's a heavy fermion superconductor class. There's a lot of other materials here. There's just a lot of different superconductors that have been discovered in the last few years. You can see this line sort of separates old superconductivity from what's going on now. Now, why are we so excited by this? Well, first of all, it's new physics, and that's what we're really about, discovering things that are new. We want to engineer new applications. So some properties of these materials that are interesting. They're ceramics. They have higher TCs than could be explained by conventional superconductivity. They're low dimensional. They have strange properties. They have a weird doping dependence. You start with something that's an insulator and you put things in it. Defects. You add defects, it makes it better, makes it superconducting. What I've been talking about really is not any of this, but just the superconducting state of these materials. So I want to say just a little bit about what makes them exotic. And then I'll move to a couple applications and we'll be done. So first of all, they're unconventional in that they're not like a BCS superconductor. The pairing state is not symmetric. It has a different and anisotropic pairing symmetry. Symmetry is a very important word in physics. Symmetry talks about how systems are invariant under various changes. Is it the same if I translate it? Is it the same if I rotate it? Is it the same if I reverse time? Inverse the parity? All these various things. And this characterizes what we call the pairing symmetry, the order parameter symmetry of these materials. And you might be familiar with, how many people know SPDF from chemists? Chemists certainly knows this, right? Yes? So these are different symmetries. They have to do with how things change in sign as you change direction. And what we were able to do in a series of experiments, and I'm not going to have time to go through a lot of them, but we were able to show that this material has a D-wave pairing symmetry. And I'll leave that guy out. How many people? Charlie Schlichter actually was the one who limited the number of choices here. There became a big debate about what the symmetry was of these materials, and it was actually determined to be D. And we did this by a series of experiments. I'm going to skip some of this because I'm running late in time. Okay, I'll show that one. So we proposed an experiment by which we could actually measure the sign change doing a interference experiment. And this enabled us to determine S-wave parity from D-wave parity. And I showed this picture because how many people know the book Don Quixote? Yeah, great book, right? He goes on a quest to destroy windmills and things. So I had my own team of people to do these experiments. Dave Woolman, a graduate student, Don Ginsberg, who grew the materials, and Tony Leggett, you might know, is the only Nobel laureate at the University of Illinois. And so we set out to do an experiment. I'm going to skip some of this because it's not so relevant. Oh, this is a picture of my group meeting back in that time. This is in the early 1990s. And what we did, it was a very simple experiment in which we took the crystal, put junctions on different faces, and by making a device like this squid device that we've been looking at, we could actually tell by interference experiments if there was a phase change between these two directions. So the idea was if it was S-wave, you would get a modulation pattern such as this, which is analogous to this pattern I've already shown you. If it was D-wave, it should say, I don't know why that says P, D-wave, then you get a sign change here, and that would put a 0 in the magnetic flux at this point. And those experiments done by Don Ginsberg and other people, this is a picture of the crystal. Crystals are very important in this field. So here's a picture of the single crystal of yttrium, barium, copper oxide, this high temperature superconducting material. So this material then was measured in these squid configurations, and I should just tell you, this is an actual picture of the crystal. It's very, very small. That's why I need graduate students to be able to see these objects. They're the eyes and ears of these kind of experiments. So here was the actual experiment, and it did in fact verify this sign change of pi between orthogonal directions, direct evidence for this D-wave symmetry. So these materials are not only higher transition temperature, they are totally different animals. And they are defying us. So at this point I should tell you, why are these materials superconducting? I can't. Because that is awaiting the next Bardeen, Cooper, and Schrieffer discovery. We do not know yet why these materials are superconducting, although it has been a topic of debate for 23 years now since the discovery of these materials. This is what a lot of the people in the Department of Physics here and elsewhere are spending their time doing. So this is just another experiment. So what's the significance of these experiments is that they actually showed this D-wave symmetry, and they pioneered a technique which allows us to look at lots of other superconductivity devices. I want to mention another thing that they did is they talked about, they actually were a good example of how we do physics in this department. It's actually across the country, if you go around, people refer to what is known as the Urbana style of doing physics. What that means is you're not just theorists or experimentalists or sample growers. We actually we pick a problem such as this, and notice we had a whole team of people working on this. So we work together in this mode of doing research. That's a good thing. It makes it doable, it makes it fun, and it actually allows us to address problems that other groups do not make. So superconductivity, as Naomi pointed out at the beginning, is a problem which is really quite synonymous with the University of Illinois. It's one in which we kind of defined our style, and one in which we are still making a lot of contributions. I want to show this very quickly here to show you that things are actually expanding. Here's some other materials that are known to be D-wave. There's things that have a different symmetry, anisotropic D-wave. There are materials that it's not important exactly the details, but these are things which have even higher symmetry classes. P-wave, which means odd symmetry. These are things that have broken time reversal symmetry, complex states. Almost every week, it seems like. I just came back from a meeting in Japan, in Tokyo, where they had a whole new class of superconductors that have been discovered. Let me show you those. I'm going to skip these because these are more detailed for the moment. So I do want to show this. So these complex superconductors, we've actually had some papers where we were able to study a material called strontium ruthenium oxide. It's a low TC material, so I can't demonstrate it here. But we found that it actually has this very interesting symmetry where the phase is not positive or negative, but actually changes continuously in space. And this is called a chiral superconductor, or a P-wave, or a complex superconductor. These are important because there's a lot of new physics, but the important one that I want to get to, so as I said, this is where I define the title, exotic superconductors, because there's materials we're discovering that have properties that we have not ever seen before. It's in many ways a culmination of a long personal search for me. We've been working on this in my group for about 10 years or so. Finally have been able to discover these materials. It's important for funding. When you get results, the funding agencies like this. But one thing I want to point out is one of the really perhaps interesting technologies that might come out of this is what is known as quantum computing. There's a way with these materials to create materials that are what are known as topologically protected, so you can do computing without the dissipation that normally messes up the quantum computing. I just want to mention that just this last year there was a whole new class of materials discovered in a material which actually contains iron, and you see for the first time, I think, the coexistence of superconductivity and magnetism. And here is already the family tree for this, and notice this is now measured from 1907 or 2007 up through just about 8 months, and all the materials that have been discovered in this class. So superconductors are being discovered at a very rapid rate. There's already 4 different families of these materials involving iron, lithium, arsenic, and these are all materials that we have to play with in our toolbox. Okay, last thing I want to mention here is the real driver behind superconducting research, and that is the power grid. This is a picture of the power grid. There's actually 3 power grids in the United States that are connected together, and these are the trunk lines that carry power. We expect a 50% growth in the capacity of electricity in the next 20 years or so. About 10% of the power we generated is lost in transmission. When you carry current through wires, copper wires, there's heat dissipation. And so superconductors, this is just a picture showing this demand. This is the world demand for energy. We're about right in here. And so you can see or measured from this point, we expect it to increase by factors of 2 or so in the next 20 years. So there has been a number of studies done by the Department of Energy. This is an example of one of those basic research needs. And the key point is that superconductivity has the capability to transform the power grid by carrying current without dissipation. And here's an example of the present generation of superconducting wires. They're fairly complicated. The active part is this black one right here. That's the high temperature superconductor, the ceramic. And then the rest of this is there for stabilization. This is from a company called Superpower, which is in Schenectady, New York. So here's what we're trying to do. We're trying to make materials which have a high critical temperature, a high critical current density, that are isotropic, not layered. They're S-wave, not P-wave or D-wave. They have a simple phase diagram, and they make good wires. So far, when we discovered things that have high temperatures and high current densities, they don't have any of the other things. So the cuprates are wonderful, exciting materials, but you can tell it's not going to be easy to make a wire out of something that looks like a charcoal briquette. So there is enormous work to be done, and one of the things we're doing is President Obama started the DOE Energy Frontier Research Centers. We were fortunate to win one of those here in Urbana, in emergent superconductivity. It's a partnership with Argonne National Lab, Brookhaven National Lab, and 2 prominent superconductor wire companies. And our goal is to try to find the next material that's going to transform the power grid. It's an important challenge. There's things being done. Here's some examples of power lines already in existence for trunk lines, short distance run power lines. That's where most of the power is lost. Another big application is you can use superconductivity to make motors and do wind power. These are for offshore and in prairies such as this, wind turbines that generate power, and they're much more efficient than ordinary turbine materials. So I've come sort of to the end of my story. We've gone through lots of discoveries, lots of materials, lots of ideas here. What have we learned? Well, I think what we've learned, what I've tried to convince you of, is that superconductivity continues to thrive after 100 years. It's not dead, as I was told when I was in graduate school. It's not dead, as I was told by a funding agency right before the discovery of high-temperature superconductivity. More and more materials are being discovered. Except for the classic superconductors that we sort of explained a little bit how that might work and is understood by BCS, we do not know the mechanism of superconductivity in these other materials. So we're still seeking that. There are many applications, and I've mentioned some of those: power transmission, medical, imaging, magnets, things of that sort. Discovering new superconducting materials is a major challenge of our generation. It is believed by many, Department of Energy for one, that superconductivity has to be part of the solution. It's not the whole solution, but part of the solution of creating a sustainable energy environment in our country. One thing I hope you learned is liquid nitrogen is really cool in a couple of different ways. And finally, physics is a lot of fun, and I'm happy that you've joined us here today. So thank you very much. So I'm happy.
I noticed on your periodic table there was a yellow for carbon as opposed to green and blue. Is there a reason for that?
Let me go back to the periodic table because I don't remember that one. Okay, so we're looking here. That's a good question. I didn't make this chart. I'm not sure what. So carbon is interesting because there's controversy, maybe that's why it's there, on whether carbon becomes superconducting or not. There are people studying graphene, which is single sheets of carbon, studying carbon nanotubes, and there is controversy right now whether you can induce superconductivity in those materials. It is thought that if you dope them, there are many theories, there are no results yet, if you dope them like you dope cuprates, put in impurities, you can make them become superconducting. But I'm actually not sure why that's yellow. It's not on the key here either. So, question over here. Do you have a question? Yeah.
How does the Cooper pair manage to move if it needs that plus in the middle to keep it a pair?
So the Cooper pair is actually driven by things like vector potentials in the material. So a Cooper pair normally is made up of 2 electrons which have opposite momentum. So they're going in opposite directions. So intrinsically they carry no current. But when you apply a phase difference, which you can do by, say, applying a magnetic field, that's what I'm doing when I wave the magnet along, then you actually you can actually accelerate the Cooper pairs. You can apply a force that accelerates both electrons, and then the Cooper pair can move through the material, and it does so without dissipation.
But what does it do for that plus? Does it take it with it? Or
Oh, no. So the pluses are fixed in the lattice.
so it swaps it out? As it goes?
Well, so the electrons in any conductor, what happens is the electrons are free electrons. They can move. They're not bound to the nuclei any longer. So a lot of the electrons are, but what we call the conduction electrons are free to move. So the Cooper pairs are made up of the conduction electrons, which are free to move through the lattice. So they don't drag the pair with it. So it's a little more complicated than what I said. What happens is the pairs form, and then they move on to the next pair, and so it's a dynamic pairing. So the pairing actually is, there are lots of terms for this, but basically it's it's a time averaged pairing. So the important thing is that the energy is lowered. They spend some of their time in proximity, which lowers the energy of the system, but they're not bound up like you have to resist thinking of it as a physical space pair, where these two things are glued together and intrinsically moving through. So what happens is, in fact, that due to lattice vibrations, the lattice perturbs, so you get a small buildup of positive charge, the electrons are attracted to that, then the phonon goes away, and the electrons continue to move through the lattice. It's actually an interesting question, because the hardest thing to do in superconductivity is to actually explain why there's zero resistance. Of all the things that are, there are a lot of things that are very well understood. That's the hardest one to explain. And it really has to do with it forms this quantum state where the lowest energy state is one in which you have a current carrying state in the material. Yeah.
Is there any accepted search strategy for new material?
Accepted, I don't know, but we have one in our center. So I should say that most of these discoveries are not just accidental. This is not alchemy. So the people, Bednorst and Mueller, discovered high-temperature superconductors. They were discovering a set of materials that was known for many years, lead, barium, bismuth oxide. There were some oxides around, and they knew that they were superconducting. They were studying their properties, and then suddenly got to higher transition temperatures. The people studying the iron pnictites, they're called. Pnictites means in proximity to nitrogen, so it just means things with materials in the same row, or same column as nitrogen. So those people were studying these materials for many, many years because they actually can make transparent conductors. So the idea is you can make materials that are transparent and you can put electric currents in them and change them, much like liquid crystals or something. So we have a plan, actually, in our center. That's why we got the money to do this. What we do is we look at the periodic table and we said, well, if this and this works, then this and this should work. So it's a bit, it's exploratory synthesis, but it is targeted. You have ideas, you pursue it, you go in these directions. But there is no guarantee. No one predicted the Coop rates, and our guess is no one will predict the next generation of materials. Which one? Oh yeah, sure, we can do that. We ought to blow something up. I think the truth was I was too scared to do it. I thought it was going to blow up in my hand. We need mats here, don't we, to do this? I was told not to put in too much because otherwise I'd take out the projector screen. All right, so let's do this a little better here. What? We'll take out the... Yeah, it just cracked. Unfortunately, it's still cracked. The answer is no. I can't do that experiment. We'll just pour some nitrogen on the floor.
Okay. One more question about it.
Yeah.
What temperature did you say that the ceramic becomes superconducting?
Okay, so there's a whole lot of them. So the highest temperature known is 160 Kelvin. That was in 1986. So the first one, let me show you the graph again. You can see all of them on this picture here. I go back up here. Well, that'll answer the question there, isn't it? Yeah. Well, so much for that. So I was told to put warm water in it so it would make it blow up faster. And I thought, no, I don't think we need to do that. Ooh, that was good. So it did work. Wow. I told you, experimental physics is a hoot here. The element of surprise, right? Okay, so let me actually, probably the one to look at here is, I'm not finding the right picture here. Okay, well this was the cuprate. So you can see in the first, this was just so the discovery, the first material was December of 86, was actually 35 Kelvin, but it went up very quickly within a few months by February of 87 to about 90 Kelvin. That was the discovery. The material I was levitating magnets off of is this yttrium, barium, copper oxide material.
Oh yes, over here on the left. I was wondering, like, a lot of the superconducting materials that you were showing on the screen were more solid-looking kinds of materials. Are there any that are like liquids or maybe gases even, or like, can you have a superconducting material as a powder?
We don't know of any, well, I should say neutron stars are actually thought to be superconducting in a different way, superfluid. But in these materials, they're all solid. Now, mercury, of course, is a liquid, but not when it becomes superconducting. So, but there are a variety of interesting materials. There are organic materials that are superconducting. There are layered materials. There are, as we see now, magnetic materials, ceramics, of course, metals, nice metals. I should point out, I meant to point out actually, to come back to it, is I didn't come back to the periodic table and say why copper, silver, and gold do not become superconducting. And the reason is that they do not have this, one of the reasons that they are good metals is they don't have this strong phonon coupling in the material. So they don't have the necessary ingredient to create the superconductivity. So it's a bit of a paradox that the best materials at room temperature that are not superconducting materials do not become superconducting. Things like these ceramics, which are actually horrible conductors at room temperature in ordinary metals, become superconducting at lower temperatures. So there are clues all over to what's happening here. It's actually believed, I shouldn't be so harsh, I mean there's a lot of theories. David Pines, who was a theorist in our department for many years, just won a big award at this meeting in Tokyo. And he announced that we know the mechanism for high temperature superconductivity. We just don't know which of the theories is the right theory for this. There are many things that are proposed, and I think the prevailing view is actually a magnetic coupling. The interplay of superconductivity and magnetism I hinted at in this talk, but it's actually very interesting. It's generally thought magnetism destroys superconductivity, and they're mutually exclusive, but in fact we're beginning to think they're actually strongly coupled. And that's probably the mechanism that creates the superconductivity in these more complex materials, yttrium, barium, copper oxide.
Is there any thought about the upper limit of temperature for superconductivity?
Well, that's interesting. It's like one of those moving targets. As when I was in graduate school, we were told the limit was 35 Kelvin. And of course, that got eclipsed. And then we said, well, it must be 160 because we plateaued, and that is still holding. Most people believe there is no intrinsic limit. There is no reason why superconductivity could not happen at room temperature. It's a question of balance. It does get more difficult because you've got to counteract all these thermal fluctuations that are existing in the material, but in the system. I should say to make wires, we don't really need higher temperature superconductors. Anything that works at liquid nitrogen temperature or higher will be fine. You can liquid nitrogen is actually not very expensive. It's cheaper than Diet Coke, so you can. Yeah, I think so. But I wouldn't drink it, although I've seen people do that too. So that's something that could be overcome. The real problems are these other things I listed: the fact that it's two-dimensional, it's layered. The fact that it has this odd, the thing that makes it interesting, the funny thing is the thing that makes it interesting for me, this exotic pairing, the D wave, P wave, complex pairing, makes it a bad material for carrying wires. What you really want is something that's ordinary, boring superconductor like lead, niobium, except with a high transition temperature. And it's not clear if that's possible. It may not be possible.
Your positive ion has a question.
Yes.
Where can you get liquid nitrogen?
I just go down to the corner of our lab and there's a tank, and I think it's liquid nitrogen. We actually use liquid nitrogen. We have a liquefier to make helium, and we buy liquid nitrogen. It comes in big tanks. It sits outside back of Loomis lab here if you want to. And we keep a lot of it in the building because we use it for lots of experiments such as this. It's also used, of course, extensively in things like a lot in hospitals who also now use liquid helium because of magnetic resonance imaging. There are superconductors are all over in magnetic field applications. So where can you get it? I don't think you can get nitrogen at Walmart, can you? I just don't think. Yeah, I think so. Well, the fact that Diet Coke doesn't do this when you put it in a bottle, I think it would be rather dangerous, as we've learned. I can't even hear.
Is there one more question?
Or I was going to say, you can get it at the Red Cross. They actually sell it. That's dry ice. No, dry ice.
Yeah, I think you can get dry ice easily, but nitrogen is harder because you do have to store it in containers, and it is rather dangerous, as we learned. You can actually burn yourself quite easily with it. It's very cold. But, if anybody wants to come up and play safely with it, you're welcome to do that after the
And the other way
lecture.
to get it is to come and join us and become a physics student.
There you go.